Here we have a goodness of fit test, and this is slightly complicated, so let's look into this. So what is a goodness of fit test? And let's say a company, right? Like I guess M&M's here. We'll use M&M's. And also, I don't know why I have a percent sign here. It should be an and. I like M&M's, so I don't know how I got that wrong. But they come in these percentages: 20% red, blue, yellow, green, and orange. So simply put, there's a 20% chance for your M&M to be red. And I don't like the word chance, so I guess I'll say 20%. 20% of your M&M should be red. So let's say you count 100 M&Ms and you get 30 red. That's 30% red, 10% blue, 20% yellow, 25% green, and 50% orange. Do the results match the 20% each? And the simple answer, as we look at this, is no. But also, we can't understand if it's an outlier or not. So we don't know if this is an unusual M&M standard here. We don't know if this is some mistake by the company. So here we're just going to use the goodness of fit test. And that basically is hypotheses. And let's go over this again because it's different for each one. So the null hypothesis is that the company is correct. There's 20% M&Ms in each bag. And I don't like how the null hypothesis differs. Like sometimes they'll assume the drug doesn't work, and sometimes they'll assume the company is correct. I mean, shouldn't the company prove that there's 20% M&Ms in each bag? I don't know. Maybe that's a question for a statistician. Um, but I guess this is only simple statistics. So now the alternative hypothesis is that it's wrong. There's not 20%. So let's choose a significant level. Now, say there's 0.5% chance. You're okay with being wrong. I don't know why I said significance level. Okay, I guess that works. It's the alpha. Again. So the reason why they say a 5% chance you're okay with being wrong, and I want to make this clear, is because in the distribution, right, and I'll just use the empirical rule here, um, two standard deviations contain 95% of the data, but three contains 99.5. So there's a chance that your thing is just an outlier, but it's actually part of the original data set. Um, so it is a real thing, but you assume that it's incorrect because it's highly unlikely. But unlikely things could still happen. So 5% chance is the same thing as saying we only focus on the 95% that is right, the inner 95%, the middle 95%. And also, let me just draw this out because it's a little complicated and abstract to understand. There's a distribution here, and let's assume this is 170. We'll use the empirical rule here. Minus and then plus, obviously. I guess we'll write plus, and then plus 2, and then minus 2. And sorry, it's a little hard to draw. So this should be 2.5, or sorry, this should be, yeah, 2.5% of the data here. Sorry, I'm a bad drawer, so we're just going to have to deal with this. So we're going to assume that if something falls in here, which is highly unlikely because most of this is 95% of the data points are in here. But we're going to assume that it's a wrong data point or it's an incorrect measurement. And we have a chance of it being wrong because it could just exist here. But we're just going to ignore all this data basically, and we're going to focus on this part only and the shaded region, ignoring the minus 2 standard deviations and plus 2 standard deviations. So that is the logic there. And sorry, let me just go back here. So now we just calculate the expected counts, and as we know, expected counts is number of trials divided by probability or proportion. So using some simple logic, we should expect 20 M&Ms per color. So we use the chi-square formula, and the chi-square formula is just the difference squared divided by expected, which kind of acts as a standardization. The expected value, we see how many expectations it is away. We see how many expectations the difference. We see how many expectations the square difference is away for each category, and then we add them all together. And now we find the degrees of freedom, which is k minus 1, which is categories minus 1 here, so it's not going to be trials minus 1. In fact, I don't know how you would do trials minus 1. I guess it would be degree freedom 99, but you're looking at this on an individual basis, so it's categories minus 1. So we look up the chi-square for the degrees of freedom, and here we use chi-square, and because we square the thing, And a chi-square is just going to be the formula observed. I think it's observed. It might be different. Yep, observed minus expected over expected. And I was going to make the fatal algebra mistake by squaring these two, but instead we square that. I mean, I guess I could use the binomial expansion theorem here, but no. So anyway, since it's squared, we could see how many expectations it is away. The degrees of freedom will tell us what the distribution is. And category is -1. So let's use some simple logic here because I kind of forgot as well. So the higher degrees of freedom, I guess the more closer it would be to the data point, which I'm not sure it's, no, it should be further because we should expect more deviation from the categories. So yeah, I guess that is the case. But anyways, you'll find something that matches up with the chi-square distribution, which is simply just this right here, just the distribution of all these points. And the degrees of freedom will tell you the probability to the right of the curve this time, I believe. So if a chi-square statistic is higher than the critical value, our result is too unlikely. Yeah. So that means we reject the null hypothesis. So it's simply what it is, and a critical point, as we know, is just a point where our confidence interval ends. We're not making a distribution. We're just comparing our sample data to an existing known or claimed distribution, which is the degrees of freedom distribution here. We are measuring the percentages of chi-square statistics. So I guess people made the chi-square statistics for other things, and that's how we did it here. I'm not really sure how they made the probability things. I'm still not sure. I was actually looking into the distribution formula, which is quite complex. I don't really know it, but it has something to do with the Gaussian integral. And as you know, that involves the Jacobian matrix, and it gives you the formula of square root pi, which is really interesting because pi comes from an integral that is not trigonometry related. But yeah, I guess pi is in everything. So the distribution of the chi-square was made using many samples, and that's how we get the t distribution and can know this. I mean, to be honest, it's getting quite repetitive with the distributions here, but just stay with me. There's only 2 more lessons left, so